minus 10, 9, 8. We have a go for main engine start. We have main engine start. 4, 3, 2, 1, 0, and liftoff. Liftoff of the space shuttle, and it has cleared the tower.
Looks like slow. It is slow. That's the Cape.
Yeah, you're your touchdown.
Hello and welcome aboard the Space Shuttle Endeavour, where we're orbiting almost 300 kilometers above the Earth. Our primary mission on this flight was to deploy a Tracking and Data Relay Satellite, or TDRS, TDRS for short. And when it becomes operational, it will relay communications between orbiting spacecraft and tracking stations on the ground. A few days ago, we sent the satellite on its way.
Houston, Endeavour.
Go ahead, Endeavour.
We have deployed the IUS TDRS.
But deploying TDRS wasn't our only mission on this flight. Two of our crew members put on the protective EVA suits and went outside the orbiter on an important spacewalk.
We also have several science experiments to conduct, but for one of our experiments, we brought along some toys. Each of these toys work because of important scientific and mathematical principles that we often take for granted on the ground.
But things can work differently in space than they do on Earth, even toys. That's why when we're orbiting the Earth, we experience something called microgravity. That means that everything around us, our space shuttle, astronauts, even toys, float as if they have no weight.
If you don't understand microgravity, your teacher can help you out. But for now, we need you to help us with these experiments. We want to find out if the toys act differently in space than they do on Earth. But first, we have to know how they work on Earth. This is where we need your help.
We want you to experiment with the same kinds of toys we have here on the shuttle. Then, when you become experts with them, try to predict how they will act in microgravity. After you've made your predictions, watch what we do with the toys and see if you are right.
Remember, this is a team effort, and we're counting on you to make our experiment a success.
In this scene here, I'm trying to get the rat to flip on my hand, but as you can see, what happens instead is that his legs push against my hand and he spins up and away. Now in the next scene, what I did was tape his feet to a book. Now the book is so much more massive than the rat that when the rat pushes on it with his feet, the book turns only very slowly, and the rat, because he's taped, cannot jump up and away like he did with my hand.
Watch what happens when the suction cup releases now. You can see the spring jumper takes off. We'll watch it again. And boy, look how fast that travels across the spaceship. It really surprised me. We'll watch it slow motion here, and you can see it tumbling coming off the lockers.
The big question with this scene is, will the frog swim as well in air as he does in water? Well, if you watch the picture here, you'll notice that no, he does not. I try all different ways of getting that frog to swim in a straight line, but because the air is much less dense than water, I can't get him to do it. So the frog just flops around.
We'll take a look at the submarine here, and I'll let it go, and you can see that as it turns through the air, both the propeller and the submarine turn, instead of in the water where only the propeller turns. Now I'll take a look at what happens if I hold on to the propeller, and you can see that the submarine turns around it. Then I'll let both go, and it takes off. One more time. This time I've attached small pieces of paper onto the propeller to make the propeller larger. And we'll see what happens when we let this go. I'll move back so we can get a greater view of the line of travel. Let it go and it really takes off.
We've taped a pen onto the end of the submarine propeller to see what would happen and if the submarine would change the way it moved. Well, it turns out that it did. As you can tell, it flops around quite a bit more, and we had a harder time keeping it under control.
Let's look at the swimming fish. Now this fish swims real well in water, but watch what's happening now. He's really struggling and not getting anywhere. Just sort of floating around. Really doesn't swim very well in air. We'll try it one more time. Whoops, I think I had a little rotation, and he's turning around, just sort of flopping around, not really getting anywhere, trying to swim through air.
One of the things you can do to help the fish swim better in air is to increase the size of the fin. It also turns out that releasing the fish very gently has an impact on which direction the fish will swim. I finally got it right in this scene here, and you see the fish swimming forward.
We'll look at the flapping bird in microgravity, and you can see what happens here. It just flies around in circles, doesn't seem to have any direction of travel. Let's look at it again in slow motion. Just goes around, doesn't go straight as it does on the Earth in one gravity. And it looks like it's turning around the wings. Now I'll just soar it without the wings flapping. And it soars across the middeck. I tried throwing this paper maple seed several different ways. You can see it didn't go very well when I threw it holding onto the wing. Now I held on to the bottom and threw it, and it turned just a little bit. I finally got the hang of it, and you can see it turning now very much the same as it does on Earth. I'm throwing the paper boomerang, and we'll see what happens. It goes into the side of the wall. If there had been more room, I think the paper boomerang would have come back. Now this time I threw it and flipped it with a lot of rotation, but not much forward velocity, and it just keeps going straight.
Boy, that thing shot up like a rocket, and that caught me by surprise. I didn't expect that in this microgravity environment that it would go up that quickly. Even in slow motion, it comes off and hits me in the chest even before I can react. Here I have a single graviton that's floating free in the cabin, and it's spinning. You can see it wants to spin about the wheel inside as well, so you see the outer case spinning also. But I'm trying to get it to tip over, and I can bump it on the sides, on the top, on the bottom, and I can't make it tip over. It's stable about the axis I let it go in, which is the spin axis is up and down. This is the same configuration. I've got one spinning graviton here, and I've oriented it so that spin axis is pointing at the camera. Again, I'm just bumping it on the sides and the top and the bottom, and I cannot get it to tip. It's stable about the axis I let it go in. This should be a graphic demonstration of a spinning and a non-spinning graviton. You see the spinning graviton stays stable while the other one tends to tumble end over end because it has no stable spin axis. I'll do this one more time. You can see that one is spinning and one is not, and the one that's not spinning just tumbles free while the other one maintains the orientation I let it go in. Okay, here I have two spinning gravitons, and they're both stable as they spin here. And I take one and bounce it off the other. You can see this time, because they're both stable, they don't tumble. Neither one of them tumbles, as you might expect. Now here I have a curious combination of two gravitons that are attached together on a wiffle ball. And I have them both spinning in the same direction, so I would have thought they'd be very stable in this configuration. But because they weren't perfectly aligned with each other, they got out of hand. Wham! Came apart and really gave me a surprise. Let's take a look at that in slow motion. You can see how the misalignment causes them to break apart. Now this time I took those two gravitons and I rotated them in opposite directions from each other. And because their angular momentum vectors are in opposite directions, their stability axes cancel each other. So I'd expect to be able to let this go and just have it tumble. Now obviously I can't make them both spin exactly the same speed, so the one of them is going to have a little bit of stability, but you can see I can bump this stack and I can make it wobble around a little bit. As I bump it here, you see it will wobble some. It has some tendency for stability, but not as much as a single graviton would have floating on its own. I can make it wobble pretty wide end over end. So having two of them spinning opposite directions canceled each other. Now we're getting complicated. I have three gravitons all hooked to the same wiffle ball, orthogonal to each other. That is, their alignment is 90 degrees to each other. And I'm going to spin them all in the same direction with reference to their attachment to the wiffle ball. Now, as I do this, you would expect that the angular momentum vectors of each of the gravitons would add up to a single vector which would be right between all three. So as I let this go and it tends to rotate, the only axis that it will rotate around is an axis that you can see if you put a pencil between all three of the gravitons. It's rotating about that axis that's equidistant from all three of them. Now as it continues to spin up by the natural character of the friction in the gravitons, it eventually spins up so fast it comes apart. Well, here's the same combination again. I have three gravitons mounted orthogonally to the wiffle ball, and I'm going to spin them all up in the same direction. And before I spin them up, you can see how they tumble end over end. There is no stability there because none of them are rotating. Now, as I spin all three of them up, initially when I let them go, you'll see them begin to rotate around that same axis that's right between all three. But one of the gravitons comes off, and look what happens to the remaining two. As that bottom graviton came off, the remaining two gravitons now are rotating around an axis right between the two of them. And again, I was lucky I didn't get beamed by this graviton as it came off toward me. Now here's an experiment that's a good demonstration of how a non-spinning graviton behaves just like a ball on the end of a string. I can change the axis of rotation just like you could with anything attached to a string here on Earth. But once I spin this graviton up, look how it maintains that stability around its rotation axis. I can spin it around and around, and it wants to stay in an orientation so that the spin axis is parallel to the axis of rotation that I'm holding the string in. Now look how I change the orientation, and eventually the graviton ended up changing the orientation of its rotation so it matched the rotation axis of the string. Very interesting change in the way the graviton behaved. Now eventually I'll take it back to a horizontal rotation, so the rotation axis of the string is vertical, and you'll see the graviton again orient itself so its spin axis is vertical to match the rotation I'm making with the string. This rattleback is a very curious device here on the ground, because if you rotate it on a table, it will eventually turn around and spin the opposite direction. Now, what you're seeing here are 3 sequences of me spinning it around each of its axes. I spin it end over end with the thick side horizontal, and then end over end with the thick side vertical. And then in the last sequence, I spin it around its longest axis. You can just see it spins. In no case did it ever turn around and do the peculiar things it does on a table.
I was playing with the clacker balls one afternoon on the shuttle, and I had let them go and they drifted apart and they did this funny motion. So what I tried to do was get that funny motion to repeat itself. I experimented a little bit. I tried various different actions by spinning them in one direction or the other. I wound up taping the clackers so they stood apart, and then I flipped them first end over end, and that didn't seem to repeat the motion that I accidentally had discovered. And then spinning it around along the axis of the handle produced the flipping motion that you see here, and that was quite remarkable. As it spun around, there was a little bit of imbalance, and it seemed to flip end over end, which was unexpected when I first took them into space. Before flight, I had to practice with the clacker balls a bit since I had never played with them before. I became quite proficient at using the clacker balls in this fashion. However, while I was able to get one ball to displace the other on the ground, I was never able to get the clacker balls to do this in space. It was more difficult to produce this motion with the balls in this orientation relative to my body. In this next orientation, it was a little bit easier to get them to even come close to displacing one another, but I was never really successful. I believe it was easier here because of the orientation of my arm relative to my body made it just a bit easier in getting the balls to behave as I wanted them to. On Earth, gravity produced just enough drag on the stationary ball by weighing it down just enough so that you could produce the desired motion. That is, have one sit still and the other one spin around and hit it, and then it staying still and the other one continuing the motion.
This experiment is a demonstration of the concept of momentum. The racquetball has less mass than the pool ball, and as a result,